That's really scary. Also, what would you say? Okay. Okay.
Did anyone not get a homework return that was expecting one? Okay, so let's get started by turning our phones off. So my plan is, there it goes. I want to use this projector because this part of the board is the hardest to read at the bottom. So I'd rather it block the slides than to block whatever we write on the board. So I'm going to do all my writing over here in case anyone wants to move. It's a huge room. I like the other room. I like that the screens were always up and never blocking anything. But we're going to try video recording, and I'm going to post the videos to YouTube, where you have to have your Bates login. And if you do that, you guys can take advantage of those videos for the rest of the semester. This allows anyone who is going to be on trip to the hospital to be able to catch up without us having to duplicate class. So I think it's going. The problem is I have no feedback, so I don't actually know if it's working. So this could be a catastrophic failure. So I hope that someone's taking great notes in case there is a failure and we have to pass those along. My notes are terrible. So if Astrid, John, Seth, or Leon are in here, then you shouldn't be. Here's the schedule for the rest of the month, and so I hope you guys remember your date. Take a look at your group. You guys know that, I can do this. So take a look at your group and make sure that you know who your friends are, who your group is, because that is the group that you're going to give your final presentation on. You saw on the syllabus that the presentation is last week of class, and it takes up a good chunk of your grade. And so that'll be an opportunity for you guys to explore topics that we don't get to cover in class, whether it be optics, with light imaging, or whether it be the non-optical imaging that will cover at the end of class, like ultrasound, MRI, and CT. So if you guys have taken a look at the homework that's posted on Lyceum, you'll see that the last problem on the homework isn't a problem at all. It's asking you to pick. And so yes, I expect you to pick a topic. It should match what your group partners are all saying, but when you turn in your homework, make sure you choose something. I gave you a list to get started from, so take a look at that list. If something interests you, sign up for it. If there are any conflicts, I might have to resolve them. So that's why we're doing it now. Otherwise, that list is not comprehensive. You can do whatever you want, as long as it's relevant. And if I forgot something, or if I didn't think of something, please choose that topic. But you will be giving that talk with your lab partners, or sorry, your group here. I obviously won't be a part of this one. Speaking of which, I will not be here on November 15th, so we will not have class. So that is a week from Thursday, and that will give you time to work on the take-home exam that I give you next week. It will be due Friday before you leave for break. Okay? I will give you more updates when I know them as to when you can actually take the exam from my hands. Okay. Let me make sure I've covered everything. Hopefully you guys saw my email that each tour of the hospital, whenever your day is scheduled, you need to be there by 3. You have to bring your badge, apparently, or they won't let you walk around. I did not realize how important it was until I got the email the other day, so I passed it along to you. Bring your badge, or they will not let you do it. And there's really no way to make it up unless you switch with someone who has to swap with you right then and there, and that's not going to happen. So bring your badge. If you forget it while you're walking over there and you remember it, go get it. Okay. No class on the 15th. We're recording the lecture. I'm going to post them. So that means that I need to also post the PowerPoints, so I'm going to do that. And the PowerPoints from last week are all up. So if you want to see what Glenn Ernstrom's green fluorescent protein talk looked like, again, it's up. If you want to see what the talk was at the hospital, it is up on Lyceum. And there's also some cool pictures up there. There was a microscopy competition that was sponsored by Nikon, people who make the microscopes over at the Imaging Center. And so the winners of this worldwide competition are up, and they're cool. They're all images taken with their microscope. There's a little bit of post-processing to make them, the colors quite beautiful. But other than that, they're really stunning. You should check them out. And then I took a few pictures of my own. I decided, reading the chapter saying that tonic water is fluorescent, I decided to take my blue laser pointer home because apparently it will fluorescent or black light. But that blue laser pointer that we have is actually 405 nanometers, so it's really violet, and that's really close to ultraviolet, and it worked. So I took some pictures. So if you guys ever buy your own violet laser pointer and you want to have a party trick, there you go. It glows quite bright blue. Okay, I think I've got everything I wanted to say. I'm going to accidentally reveal the next thing. Yeah, okay. So I should probably not leave it there because of motion. Okay. Last thing I want to say is go vote. I have not voted yet because it wasn't open when I left home, but it will be when I get home, so I'm going to vote tonight. I hope that you all vote too. And so that's it. So, do you guys remember Glenn's worms, the C. elegans worms? They were clear, right? You could see right through them. It was kind of hard to see them, actually. He played some tricks where he slid some polarizers and prisms in there. And so that's what we're going to talk about today is, what are the ways that we can see something that's 100% transparent? Do you remember when we dropped those clear gel balls into the water and they vanish? This is the problem. If something doesn't absorb light and it doesn't scatter it, what are we going to do? How are we going to see it? Well, it turns out that we have one last trick that we want to learn, and that's something called polarization. All right, so let's see if I can man this video stuff. I have no idea if that just worked. All right, so this will be fun. So polarization. It turns out that light is really an electric field. And so when we say that light is a wave, and we draw it like this, a nice sine curve, and we draw an axis here. So that wave is really the electric field changing in position or changing in time. And these arrows represent the electric field. Which I'm going to abbreviate E field. So why do I draw the electric field as an arrow? That's because it's a vector. I'm trying to be conscious of this. So a vector is a number that has a magnitude and direction. Okay, so magnitude and direction. And so what I mean by these arrows here is the electric field has this magnitude, that's the length of the arrow, and it points in this direction, that's the direction the arrow is pointing. So in this case, the magnitude is represented by the length of the arrow, and the direction is represented by the way it's pointing. What is an electric field? Well, we know that if we have charged particles, like particles repel each other, opposites attract, right? That's a force based on electric charges, and that's it. So the difference between a field and a force is that with the field you just ask, well, what's the amount of force per unit charge? But we're not going to talk about that because we're not covering electricity and magnetism in this course. All I want you to know is that these arrows point in the direction that a charge would be pushed. So an electric field pushes charges around. This is the direction that a positive charge would be pushed. Okay, so let's think about where we've seen this before. Let's say that this right here is a wave coming from my AM radio station. And I have my car antenna right here. Okay? By the time it gets to my antenna, it's going up and down. And so it's going to push the charges around in my wire that really is my antenna. It'll push them up, and then sometime later it'll push them down, and it'll push them up, and it'll push them down, and it'll go up and down, up and down, and up and down. And so this oscillation of the charge in the wire corresponds to the oscillation from the AM radio wave. Okay? And so that oscillation can be picked up and converted into sound, and we hear it in a speaker. Okay, so the idea is that if it's oscillating in the plane of the board, so you see how it's going up and down here? It's first going up, and then down, and up, and then down. And luckily my antenna for my car is also up and down so that the charges can move around. It goes up and down, up and down. And so the energy from this wave gets absorbed by the charges in the wire, and it disappears. So this absorbs the AM radio wave. Okay, what am I saying here? Who's used rabbit ears before for television? Well, I use them now. I'm too cheap for cable. Get lots of stations, and the direction that you tilt those antennae matters. And that's because you need it to line up so that these electric fields will push the charges around in your antenna. Okay? And so if I had oriented my wire into the board, the electric field's oscillating in this plane, but if the charges can only move in this plane, then they wouldn't move at all when the wave came along. And so I would want to reorient my antenna. Okay, so let's bring this back to light. So light is an electric field. It has a preferred direction. And if it oscillates in one way, it's called polarization, which is what I've already written. And so in this case, the polarization is vertical, meaning that the electric field is going up and down in this vertical plane. It's going up and down. And I've assumed that it's traveling to the right. So what you'll notice with these kinds of waves is that the direction of travel is always in one direction, and the direction of the electric field is always perpendicular to that. And so light is an electric field, and it's also a transverse wave. Transverse wave means that the electric field is always perpendicular to the direction of motion. So the light wave is going that way, the field is always perpendicular to that. There's another field called the magnetic field, and we're going to ignore that because for the most part it doesn't do much, at least for what we're interested in. Okay, so light is a wave, and if it's oscillating like this, it's vertical polarization. If it's oscillating like this, that would be the opposite. It would be horizontal polarization. And both of these are examples of linear polarization. And so we have to start thinking in 3D now. It's a little bit challenging. So from the quiz, you guys might recognize some of these terms, and from the reading. So examples of linear polarization are vertical and horizontal. There's another type of polarization, and that is called circular polarization. And so that is what's shown on the screen. Let's see. If I can do this. Okay, so we've got circular polarization here. The idea is the electric field, take a look at this circle right here, the black circle that's not moving. There's an arrow that's kind of spiraling around. I've stolen this from Wikipedia because I needed a nice animation. And so this is also considered polarized. Even though the direction of the field is changing from vertical to horizontal and everywhere in between, what actually makes something polarized is when it is predictable. Okay, so this is predictable. It's always going around like this. And so it turns out if it's moving in this direction, we point our thumb in that direction. It's curling this way, so this would be right-handed circular polarization. So this circular polarization can be right-handed or left-handed. Okay. This is polarization where the E field direction is predictable. But most of the time, we don't really care. Light coming from up here, from up there, it's thermal. If we're talking about incandescent bulbs, everything's random. And when the polarization is random, and it's not predictable, we call it unpolarized. And that would be random. It's in all directions at the same time. You can't predict where it's going to be at any given moment. And so it's really hard to do interference experiments with unpolarized light because the light's all pointing in different directions and it won't interfere. Okay, now that we've got our terms out of the way, we can have a lot of fun. Because polarization is a very cool phenomenon. We've seen it before. If you've ever been to the movies, and you steal the 3D glasses from Disney World or wherever I got these. That's where those are from. And then the newer ones look kind of like this, the big black ones, right? And what about the old ones? Here are the old ones, right? So I don't know. See through. Kind of. So what's going on here? Somehow we're taking advantage of polarization with these glasses. And so first I want to talk about how to take advantage of linear polarization. So in order to pick off linear polarization, we use something called a polarizer. And I'm going to call it a linear polarizer. And it's essentially made up of a bunch of thin wires. And they're all parallel to each other. And you take this polarizer and you embed it in plastic or something clear. And that's it. Okay, so let's say that my board is made up of these thin wires all parallel to each other. Using what we talked about with the AM radio, if I were to send a laser beam through this polarizer, what would happen? If my laser beam were polarized in this direction, would it go through it or would it be absorbed? I'm sorry, I can't hear. Absorbed. Why? If the electric field is oscillating in this direction and it meets these wires, then it will push the charges up and down, and it will lose its energy. The charges will absorb that energy from the light beam and it will convert it into motion of the charges. And then the light's gone. Okay? And so that's what's going on with this. So this big sheet here, even though it's kind of dirty, this is a polarizer, a linear polarizer. It's called a Polaroid, but I don't want to use that because that's confusing because that became a brand, which also started to talk about cameras, which has nothing to do with this. So this is essentially a sheet of little wires. And so if I hold this carefully in front of the laser pointer, the laser beam, it's gone. So not everybody can see that, so let me try this. So if I hold this in front, it's gone. And if I hold it this way, it goes through no problem. So there's a problem with this one. This thing slowly changes polarization over time. So it's a really bad example. But I should be able to put it in one way and you still see it. And I should be able to rotate it and you don't. And that's because in one case, the energy is being absorbed by the polarizer, and in the other case, nothing happens at all. It passes right through. So what happens if I take my flashlight and shine it through? Take my flashlight, it's this bright right now, so I'll just put it here. I'll put it here. It's this bright right now, then I put this in front, and it's half as bright. That's because this is unpolarized. So if you think of an unpolarized light source as pointing in all directions, then this will only let through half of them. Because half of them sort of point up and down, and half of them point left and right. You put those all together and you get every direction. Stick this in front and you get only half of them. Okay, so this is essentially polarizing the light through absorption. It's absorbing the light by making it push charges around. Okay. So how are we going to use this? Well, it turns out that we can find out if something changes the polarization of the light in a microscope. So if the sample changes the polarization, we can detect that. So the first step towards setting that up is to have two polarizers, one after the other, and to see if the direction of the electric field changes. Okay, so here's my light coming in, and here's my polarizer number 1. And here's my polarizer number 2. Draw this. That was pretty bad. Okay. So I'm going to call this polarizer. And for some reason, by convention, the second polarizer is always called the analyzer. But they're both polarizers. They're both this. They're both linear polarizers. Okay, so let's say that instead of describing the polarizer by which direction the metal strips are pointing, we're going to describe it by the direction that the light needs to be transmitted. Okay, so we're going to say that this has a transmission axis. Okay, and in this case I've drawn it vertically. And so what I mean by the transmission axis is if the light is polarized in the same direction, then it will pass through. It will be transmitted. And so let's say that I have vertical polarized light coming in. It will go through no problem. Okay? All right. Now, let's say that the analyzer is set up so that the transmission axis is looking for horizontally polarized light. So I have vertical light meeting something that's looking to pass vertical light. It wants to transmit vertical light. It goes through 100%. It reaches the next polarizer. The next polarizer wants to pass horizontal light, but I'm coming in with vertical light. And so no light passes. Or you could say that the transmission is 0. Okay? So this is called crossed polarizers. So with the cross polarizers, nothing gets through. Why would you be interested in this? Well, if any light gets through, that means that your sample, if you put it in between these two, did something. It changed the polarization somehow. So that way you know that any light that makes it out is because of your sample having some interesting characteristics. This is exactly how a liquid crystal display works. So let's take this guy and spin it around. Okay, so those of you at home, if you have a LCD screen, this will work. So LCD monitors work exactly this way. There's a polarizer in front of a backlight, and then there's a cross polarizer on top. And so normally this would be black. But in between the two cross polarizers are liquid crystals. And those liquid crystals, you can change the voltage and change the way they point, and you end up rotating the polarization. We'll get to that later. But this is an example of cross polarizers that we use all the time. Okay, so how do I know it's polarized? If you ever want to check if something's polarized, you just grab a polarizer. Does anyone have polarized sunglasses? Yeah, so if you have polarized sunglasses, you can do this. Put your polarized sunglasses on while looking at the monitor and rotate your head. And if you find the orientation, the right orientation, you will rotate your analyzer to block all the light. So let's see if we can do it. So is it this way? No. Is it this way? No. So let's rotate. Okay. So it seems to be at 45. And so that's why you can probably wear your sunglasses and look at a monitor, because your sunglasses are probably horizontal or vertical, and we'll figure out which one later. Okay, so I'm able to make this go black, right? That means that the light coming from the screen is polarized. Okay? So we have polarized light coming from LCD screens. Okay, this is a microscopy course. but I don't have any microscopes in here. So we're gonna look at something big. So here's a plastic tape dispenser, right? It's clear. If I didn't get chalk all over it, you probably wouldn't be able to see very much, okay? All right. So I'm gonna put this here, and then I'm going to rotate the polarization. And so, I don't know if you guys can see. I'll try to turn it some more. Stand on this side. So we have polarized lights. Oops. Okay, so I'm probably scratching everything. So stressed plastic, it turns out, this, if plastic's nice and smooth, it doesn't do anything, but if it's been stretched in any way, it tends to rotate the polarization of light. And so that's what I was doing with this tape, is I knew that I could do this with a polarizer and I could see cool stuff. Okay, what about the 3D glasses? What's going on there? We now know how polarizers work. We know how linear polarizers work. So the old way of doing 3D movies is you wanted to see one thing with your right eye and one thing with your left eye that were slightly different so that it looked like it had depth, so that your eyes are trying to focus somewhere into the screen. And so we did that in the early days using red and blue filters. The red signal would be for one eye, in this case my left, and the blue signal would be for my other eye, and so then the color for these movies were terrible, but I'd see it in 3D. Okay, at least my eyes would think I was looking at something in 3D. The next wave was these guys. And so this is Disney World and Magic Kingdom and what else? Universal Studios. I'm from Florida, so this is what they would give you. And everything kind of looks shiny when you wear these. I don't know, I can pass these out. If you guys are interested. And if you're not, you'll just pass it around. Everything looks kind of shiny. It's kind of obnoxious. And part of that has to do with the fact that this is a linear polarizer, and we'll talk about reflections being polarized. But these didn't work very well. Everything looked kind of weird, and if you were sitting at the wrong angle, it didn't work as well, and so you ran into all this trouble. Actually, can I borrow one of them? So, let's see. I can do something like this. No, I'll just do something like this. So, ignore the colors. And so I can actually hold these in such a way that I can make no light go through one of them, right? I can hold it, and it goes through just fine, and then it doesn't go through that one, so I'll stand over here. And so here's the 3D glasses. So I can slide these back and forth. And so what's going on here? These are cross polarizers. They're just not on top of each other, they're next to each other. So your right eye is seeing one polarization, your left eye is seeing the other. And if you have special projectors, then you can mix these, and they both hit the screen at the same time. And so then one eye sees one thing over here, the other side sees the other thing over here. That's called parallax. And your brain converts that into a 3D image. It's kind of cool. But these didn't make for very good movies because you had to be sitting right in the middle of the screen, otherwise reflections became a problem. So then they came out with these. Right, so these are the new ones. Nice. Okay, so let's see if I can try my trick again. All right, so here's this one. So if I hold them at 90 degrees to each other, nothing changes. I don't know if you guys saw that. So nothing changes here. They don't seem to block each other. It's kind of weird, right? Nothing doesn't go dark. Now what if I do this way? There we go. So that makes it go dark. That's 100% dark. 100%. So turns out these are circular polarizers. Okay. Circular polarizers are way better, and we'll talk about that. But, or I can pass these around, but you won't see anything interesting. So circular polarizers, instead of having lines to absorb one linear polarization, you actually use molecules that are spiral shaped, helix shaped, so that certain rotations of an electric field will get absorbed. And so that's actually an example on your homework. There's lots of molecules in nature that are have this chirality, and so you can actually measure that using polarization. And so that's how 3D glasses work, is it's all polarizer stuff. At home, I think that the new 3D televisions have both these types of glasses, and they also have some active glasses, where it's essentially an LCD screen on either side that makes one eye go dark, and then while the other one's open, and then it makes one eye go dark and the other one's open, and it does that so fast you don't see it, and that has to be synchronized with the television, and I think that's how those work. But as far as the movies go, this is what's going on. So movies now use circular polarizers. Okay, so let's be a little bit more quantitative. Let's take this analyzer What if I lined up the analyzer so that the transmission axes were pointing in the same direction? What would I get? Would it be 0%, 100%, somewhere in between transmitted? So I'll draw it. All right, so vertical light comes in, sees a transmission axis that's vertical, and it passes right through. Because we're talking about transmission. Okay, then if this one is also vertical, will it pass through or will it be absorbed? It'll pass through. So now it's 100% of the light, and we don't have cross polarizers anymore. Okay. Now, imagine that we're somewhere in between. So what if I rotated it a bit? So like that. I lose all the truth. Okay, so this is called, we're going to describe this using something called Malus' law. And Malus' law says that the fraction of light transmitted, so we'll call that T, is cosine squared theta. So this is the fraction of light transmitted. Where the angle theta is the angle between the two transmission axes. So the polarizer has its transmission axis aligned vertically, the analyzer has it tilted. And so the angle between those two is theta. It doesn't matter really what this one is, it's the angle between the two of them. Okay. So I think we're ready to do some of these. So now,
Wait, what's the difference? Don't we already have a fraction of light transmitted equation? Oh, is that absorbed? We did,
so we don't have anything for what polarizers do. So this is an equation for when you have two polarizers, and if they're crossed, or if they're aligned the same way or somewhere in between, this tells you how much light makes it through. Okay. Was there a question? So let's do this clicker question. I really hope it's working. Looks like somebody pushed one, so it is. So I'm going to hit this. Okay, so incident light is linearly polarized along the transmission axis of a polarizer. So it comes in and it sees something that's aligned the same way, so it will be transmitted. Okay, what is the fraction of light transmitted if the angle between the polarizer and the analyzer is 60 degrees? So everyone get out your clickers. We have more question marks than responses somehow. Let's see if I can remember my trig. Sine of 30 degrees is what? Does anyone remember? Sine of 30. 1/2. So cosine of 60 is also 1/2. And 40. So I guess now is a good time. If you can't see this, let's congregate in the middle of the room. All right, so does anyone not have their clicker?
Yeah.
One. All right, so 4 people are absent, so we should get to 18. Perfect. Okay, so most of you said number 4, 25%. So cosine of 60 degrees is 1/2, and cosine of 60 degrees and then 490 squared, because we need cosine squared, 1/2 squared is 1/4, or 25%. So number 4 is right. Okay, let's make it harder. Now the incident light is initially unpolarized. Now what is the fraction of light transmitted? This one's tricky. You can't see this. All right, so we've got some numbers here. Let's see, so 3 of you said half, and, sorry, 1/3 of you said half, and 44% said number 5, 12.5%. Okay, so what did we have last time? We had number 4, right? Last time we got 25%. So is more light gonna make it through now, or less?
Less.
Less light's gonna make it through. Let's talk about this. Okay. So now coming in is unpolarized light. That means the electric field is kind of pointing in all directions. But then it's going this way and it meets this polarizer. This polarizer only passes vertically polarized light. So essentially half of it is gone. So only half of it makes it through. Because if you think of unpolarized light, half of it being up and down and half of it being left and right, this is what it comes out to. And so half of it has made it through, and then we already know from before that 25% of whatever is here is going to make it through. So 25% times 50%, you get 12.5%. I think better in fractions, so half times a quarter is 1/8. Okay? How'd we do? Any questions? Okay, so I hope you guys are seeing the pattern. You just go step by step. You look at where the light's going, when it hits first. Okay, let's take a look at this guy. All right, I think I just set up picture-in-picture, we'll see. All right, so now, top row, we've got the cross polarizers. Light comes in, becomes polarized, sees something that's wanting polarization of the opposite direction, and no light makes it out. Okay, the bottom row here, for those of you who can see, and if you can't, please move. What we have is we have a third polarizer. So does light reach P? Does light make it out? That's what I want to know. Okay. 50-50. I like it. All right, let's work through this. Let's draw out what we have here. So if I can do camera. Okay. So the question is, does light make it through? So I don't care if this is polarized or unpolarized or whatever. Once it hits this, I guess I do care that it's unpolarized. Enjoy such moves. Okay. If this transmission axis is aligned vertically, then coming out of here is vertically polarized light. Okay? It's oscillating up and down, because that's what's transmitted when it's lined up like this. Okay, so now we have some light, and let's say our third polarizer is aligned at an angle of oh wait, we already did the math, right? Let's say it's, well, whatever, 45 degrees. Okay, just to pick a number, and then we'll do the numbers. Okay, so I have vertically polarized light here. What's going to come out? It's looking for 45-degree light. Is it going to be nothing? No. Let's do the math. T equals cosine squared to 45 degrees. This is 1 over root 2 squared, which is a half. Right? Someone shouted that out. So half the light makes it through. How is it polarized now? It's polarized at 45. So in between it's become vertical because the polarizer was vertical. This guy makes the light polarized at 45 degrees. Okay. Now we get to the cross polarizer. So it's aligned this way. What's the angle between this polarizer and the one before it? It's another 45 degrees. So it's the rest of the 90 degrees. So our second angle is this. 45 degrees. And so this means that we have the same equation as before. We're going to get a half. And so we just have to multiply all these transmission numbers together to get our final transmission. So let's say that we started off vertical. just for fun. Then 100% of the light goes through because theta is 0. So 100% goes through, then half, and then half again. And so the amount of light that makes it out is equal to 1 times a half times a half, which is a quarter. So 25% of the light makes it out. This is weird, okay? We just said that on the top row, when the polarizers were crossed, nothing comes out. But we add another polarizer and all of a sudden we get light out? It's kind of goofy, kind of strange. The math makes sense, we can follow the math, right? But this is a surprising result, and I want you to memorize it because this is a big deal. If anyone ever talks about polarization, the first thing they'll say, oh, do you know what happens when you stick a polarizer between two cross polarizers? And you're going to say, yes, I do. And it makes sense to me because I know the Malice's law. All right. So this is one way of getting polarized light is through absorption and these polarizers. There are other ways to get polarized light. I'm sorry, I keep walking over here to make sure that the camera is on. Okay. And that comment will make sense when we look at the YouTube video and the entire thing is just the PowerPoint slides instead of me standing here. Oh. Okay, so there are 3 ways to polarize light. So we already talked about absorption. And so that's governed by polarizers and Malice's law. It's also possible to polarize something through reflection. What do I mean? This is where I fly through some physics that might be frustrating, but let me draw it. Let's say I have 2 medium, N1 and N2. And I have light coming in, theta 1, light refracted, theta 2. Okay. It turns out that there's a lot of interesting physics going on when light beam changes direction like this. You've probably heard that the speed of light is 3 times 10 to the 8th meters per second. Always. But we know that light is essentially slowing down when it changes to a higher index medium. Well, that's kind of weird. Why would light slow down? And it turns out that light's always being absorbed and re-emitted. Okay. So the reason that it changes angle is because the molecules here absorb the light and emit the light in this direction. All right, so what do I mean? Let's take our antenna example. So I was talking about an AM radio antenna receiving light, receiving AM waves. Let's talk about the antenna that's generating them. Okay? So if I push charges up and down through the right size wire, I'm going to generate waves. And it turns out that the direction that they go looks like this. And think in 3D, so kind of wrap this around. Okay? If you accelerate charges on a wire up and down, it emits light pretty much sideways. Okay? This is called dipole radiation, for those of you who are interested. One thing to note about dipole radiation is there isn't any along the direction of the antenna. So if I were underneath it or I were above it, I wouldn't see very much signal. It likes to send it out, what this is saying, it likes to send it in these directions the most. That's the direction the light will come out from this antenna. Okay. So, I shouldn't have organized the board this way. Okay, so think particles in the atmosphere, and if I take charges in those molecules and I accelerate them left to right, then I will get dipole radiation like this, meaning that light will come down toward my eyes. And so, planet Earth, me, I can see blue light from scattering in the atmosphere, right? Well, if this kind of radiation, if this is the direction that light gets radiated when it gets absorbed, when it's pushed in this direction, then that means that scattered light is absorbed. So I'm actually skipping reflection and saying that scattered light is polarized. So here's the sun. It's got vertical polarizations and it's got horizontal polarizations. And the horizontal polarizations are going to emit light up and down. The vertical polarizations are going to emit light left to right. So whatever light makes it down to us, the blue light in the sky is polarized. It's not 100% polarized, it's partially polarized. So let me insert partially. It's partially polarized. So for those of you who wear polarizing sunglasses, you can probably look up in the sky and kind of tilt your head and you can see it change brightness in certain regions. And so it's thought that bees and, oh, I have another one. Homing pigeons, they think, use this because they can sense polarization in their eyes, and so they can use that as a navigational aid because they know that, oh, well, light's most polarized in this direction, and so I'm going in the right direction. It's very interesting. So let's go back to reflection. Let me get rid of this dipole radiation. All right, so let's say I have light polarized like this. So it's in the plane of the board. Okay, so that means the electric field is moving like this. And let's say that this is air. And let's say that this is something else. We'll call this just N, just to make it simple. Okay, when it gets to here, it's pushing charges, right? It's pushing charges in this direction. That means that it's emitting light like this, with nothing perpendicular to that line, okay? So no light. No light perpendicular to that line. Now that's not interesting, right? Because when we drew this, the light was going this way. Who cares that no light went that way? Well, it turns out that reflection's not as simple as we always thought. Reflection's actually light being absorbed and re-emitted. And so we have a refracted angle, so this is refraction. But we also have this reflected angle, which is going to be the same angle, right? And so this cool thing happens when that reflected angle is 90 degrees from the refracted angle. Let me write that. when, let's see here, so this whole thing is 90 degrees, and this is theta 1, and this is theta 1. So, let's see here, and so we don't know, so this is 90, this is 90. Okay, so theta,
So should the
Yeah.
refraction angle should be the one between the normal and the beam?
yes, thank you, that's what I did wrong. So this isn't working out. Theta 2, okay. Thank you. All right, so from this vertical to pointing down, you have 180 degrees. Yeah.
Is N2 greater than N1?
Yeah.
Okay, wouldn't that mean the line perpendicular to the refracted light ray not equal the reflected ray?
Right, this is not always the case.
Okay.
So let me solve this. So the reflected ray, the way I drew it, I guess is up here. Yeah? So there's a case where if you get the angle just right, the incoming angle and therefore the reflected angle is going to be, if you get it just right, it'll be 90 degrees between here and the refraction. If that's the case, these molecules are unable to emit light in that direction. They're unable to emit light at 90 degrees like those antennas. And so if these happen to line up, so okay, so all of this is 180 degrees, so that means that theta 1 plus theta 2 must be 90 degrees. So theta 2 must be 90 degrees minus theta 1. And so when this is true, we have no light reflected. Okay, we can figure out when that happens. So if N1 is 1, so I'll just write N1 sine theta 1 is N2 sine theta 2. So N1 is 1, and N2 is N, so I'll write it like this. And theta 2 is 90 minus theta 1. This is actually another way of writing cosine. Rather than deriving that, I'll just give it to you. I've got sine on one side, cosine on the other, and so I can write tan of theta 1 is equal to n. So when tan theta 1 is equal to n, then there's no reflection. And so in this case, theta 1 is called Brewster's angle. Okay? All right. So this means that, let's say we're talking about light from the sun reflecting off of a car window on your home. Okay, so if light's coming from the sun, it's unpolarized. Okay? So there's light going in this direction, and there's light kind of perpendicular to the board, and I'm going to draw that as a dot. So think of you looking at the head of an arrow coming at you, and I'm going to draw that as a dot. So light is going in and out of the board, and it's going parallel to the board. Because it's coming from the sun, it's going in all directions. But at Brewster's angle, then we have no light. And so if I were to look at the sun from a reflection at just the right angle, I won't see one of the polarizations. The other polarization doesn't care. The in and out of the board polarization doesn't care, because that dipole radiation is allowed. But it's these arrows here. It's this polarization in the plane parallel to the direction of motion. So the plane that we drew everything, it's oscillating in this plane, and so we get no reflection. And that's called Brewster's angle, that one angle where the reflected angle is 90 degrees from the refracted angle. Okay, let's see if we can show this. So here's my laser beam. It's okay if you can't see it. I'm going to throw this in front just because it's being so obnoxious with the polarization changing. Okay. So I'm going to take a piece of plastic, it's flat, and I'm going to reflect the laser beam off of this. And at some angle, I'm promising you that we're going to see no light. Okay? If the light is only moving in this direction and not in and out of the board, then no light will be reflected. If it's moving in both planes, like the sun, then only some of it will be taken out. So that's why you have polarized sunglasses. It gets rid of glare. Half of the light is essentially going to be absorbed by your polarizer just right off the bat. And then if you're lucky enough to have all the light coming at your eyes being at Brewster's angle, then you can actually start seeing through windows and stuff that used to have a ton of glare. So if you're at the right angle, you can see through the reflections off of that window back there like it's not even there, because all the reflections are going to be polarized. Okay, so let's see if I can do this. I don't have the world's steadiest hands, so let's see. I should probably do this in such a way that you guys can see. So everyone's on the other side of the room. So I should do it this way. That didn't work. There we go. All right. Here's my laser beam. Okay. So I've got a reflection somewhere. Turn the lights off. I will figure this out. Okay, there's my laser beam. And I'm going to start changing its direction from a reflection. Okay, so there it is over here on the right side of the screen. And so there's a point where it just vanishes. So it's somewhere around here, it vanishes. And that's Brewster's angle, okay? And so it's very useful for lasers because lasers are very sensitive pieces of equipment. Typically you want to put glass windows on the outside, but you don't want reflections off of those glass windows, then you lose laser power. What do? Well, if the laser's polarized, which it should be, then you just angle the windows so that they're at Brewster's angle, and then there are no reflections. Okay. All right, so we've covered 3 ways of polarizing light. We have absorption, that's the polarizers. We have scattering, we talked about sunlight. And we have reflection. In this special case where if the angle's just right, then you can get all of one of the polarizations taken out. Okay? So I should erase this now. So no light parallel to board. So this polarization here is gone. This polarization, if it was there originally, it's still there. Okay? All right, so last thing I want to talk about with polarization is this concept of birefringence. So this is a piece of calcite crystal sitting on top of some text. And that text happens to say calcite index of refraction. Okay, so we see 2 copies of the word calcite. We're looking from the top down. This crystal is transparent. It doesn't really absorb light at all. We can see it pretty well. But for some reason, we see 2 copies coming out. What's going on? So birefringence. Birefringence means that the index of refraction changes based on the polarization. Okay, so that means that if we look at horizontally polarized light and vertically polarized light, which is typically the case, these are two different indices of refraction for two different linear polarizations typically, then this word calcite on the bottom is going to have a different polarization from this word calcite on the top. So if I had a piece like this, which I will try to get before the semester's over, I could put a polarizer on top and I would see one of them, and then I could rotate it and I would see the other one. Okay? So one of the polarizations, if I illuminate this with unpolarized light, half the light will go in this direction, half the light will go in this direction. The index of refraction depends on polarization. And so if you have unpolarized light coming in, then one of them will go this way, one of them will go this way. And these are two different polarizations. So this is pretty much everything I wanted to say about polarization. So there's something called polarized light microscopy, where similar to when I had the piece of tape dispenser, the plastic piece, in between cross polarizers, and I saw interesting things. Well, this is a mix of salt and sugar under a polarized light microscope, where similar to your homework, you're going to have a polarizer over the illumination source, and you're going to have a cross polarizer over your camera or your eyepiece, so that normally you wouldn't see anything. Although I think this is filmed, this is pictured where they're lined up. But normally you'd want the polarizer and analyzer crossed, and the only light that would come out would be from the light from the polarization changing direction. So these crystals are changing the direction of the polarization. That's typically done by something called a wave plate. So a wave plate comes in two flavors. There's a half wave plate. This can be used to rotate the linear polarization. And that's essentially what these crystals are doing here. Is they're taking the polarization and then changing it, and that's how you get all this cool contrast. Okay, so there's a half wave plate, and there's something called a quarter wave plate. And if you take my 300 level optics course, we can talk about what's going on here. But this essentially converts linear to circular. And vice versa. And so if you're ever doing an experiment and you need to rotate polarization of something, you want to stick a half wave plate in. And if you ever need to go from linear to circular or back, you want to stick a quarter wave plate. All right, this is pretty much everything I wanted to say about polarization, but we're not done yet. Are there any questions? Okay, so lots of fun. After class, you're welcome to come play with my toys. And also, I didn't pass back all the homeworks for the people who came in late. All right, so let's start our last topic, essentially, before we move on to non-optical imaging. So for the rest of today and all of Thursday, we're going to be talking about light for the last time. And all the cool things that we can do with it. Okay. First, we need to talk about something called photoelectric effect. One thing we haven't talked about are detectors, the detectors that we've been using. So cameras. We talked about our eyes, but cameras are essentially what I'm talking about. And also something called photodiodes. These are things that detect light. And so the photoelectric effect is essentially when a photon comes in and it hits a metal sheet, which is your detector, and it has a bunch of electrons on it that I'm going to write as this E minus thing. And they're all stuck. And when I hit it really hard with the photon, it can absorb that energy and it can flow in a circuit. And so it'll kick an electron off, and so essentially the light gets absorbed by the electron flows, and so that's called the photoelectric effect. For those of you who care, Einstein got his Nobel Prize for this, and not for any of the quantum stuff that you've heard about, although this is quantum in itself. So the idea is that light comes in and it gives the electrons enough energy to flow. And so when electrons are flowing, that's called a current, and we can detect a current with a computer or with anything really. And so this is how we just detect light, is the photoelectric effect. And so typically cameras are going to be made out of certain materials that require a certain amount of energy in order for it to move electrons around. And so the most common detector type is silicon. And silicon will detect 190 nanometers up to, I'm going to write 1050 nanometers. So what is this saying? This is saying that light in this wavelength range has just the right energy in order to make the electrons flow. Anything lower and it's too high energy, it doesn't get absorbed. Anything longer, it's too low energy and it doesn't do anything. Okay, there are other types of detectors that you might see. There's germanium. And germanium is from 400 to 1700 nanometers. And indium, gallium arsenide, that is 800 to 2600 nanometers. And so if you ever need to detect a certain wavelength, you want to choose the right type of metal so that the photoelectric effect says that it will work. Okay, so these are the types of wavelengths that have the right energies in order to make current flow. So if you've ever seen an infrared camera, it's made out of one of the other metals. So that's how it's special. Last thing I want to say today is I want to talk about ionizing radiation. And this has to do with the photoelectric effect, because the photoelectric effect in reverse is essentially how we make X-rays. So ionizing radiation. Okay, so we talked about electrons in an atom, they're in orbits, right? And we decided we didn't want to write these orbits as circles or as the actual shapes of the orbitals. It's much more complicated. And so then we started writing things, with energy levels like this. And we said, oh, light comes in, kicks it up a level, something happens, let's say we're talking about fluorescence, and it comes back down, something like that, right? So we drew it this way. Well, we've sort of been ignoring what the top level is. So it turns out the energy levels of an atom are usually drawn something like this. And so the electron is kind of stuck in the bottom of this valley here. And for our purposes, all you need to know is that going up is higher energy. Okay, so light comes in and it can move me up into here or to here or to here. If I match the right energy, I'll be absorbed, right? Well, what happens if I get enough energy to go above the highest level? You're out. And so if that electron absorbed that energy, it's gone. And if I lose an electron from my atom, then the charges aren't balanced and I have an ion. So this is called ionization. And so this is where we'll end today. Ultraviolet light has enough energy in order to ionize certain atoms in the body. That's why it's dangerous. X-rays have enough energy to ionize certain things in your body. That's why you try to kill cancer with X-rays.
Is that why
It's very dangerous.
radiation is that way?
Radiation is bad if that radiation can start kicking electrons out of their orbitals completely, and they never come back.
Because I never understood that it has a lot of energy. Okay,
So it starts wrecking the actual atoms and molecules in the body.
that makes sense.
Oh, thank you. Oh yeah, is there another pair of glasses?
Yeah.
Okay, good.
I have a question. Do any of those work with
Do any of these work with just one ion? Is that what you just said?
Yeah.
Only the active ones that I was describing that I don't know. So these wouldn't work with just one ion.
I didn't think so.
Not for 3D. But the,
Never seen it.
the active ones
What?
that have the liquid crystals inside that are constantly doing this, you could definitely figure out a way to do that.
That'd be interesting.
I'd have to think about it.
Yeah, because I once went to a 3D movie as a kid, and I was really bummed out. It's even after I went blind, so I did not even think about it. But I was just like, oh, everything was in blue. I was like, oh, this sucks.
I can't. I'm sorry to hear that.
It was fun enough. Though I have to admit, of these two, this one does seem to work the best. That's,
You can sit anywhere
yeah.
and it would work. Whereas this polarization from reflection problem, you have to sit right in front or otherwise it
Yeah.
looks weird.
I just have sort of a question, but I think I'm noticing out and about kind of thing.
Yeah.
So I've noticed this a couple of occasions, and I asked one of my friends while I'm walking with him, and I noticed too that at night there's like a big screen window with light coming from inside. That similar to sort of like a microscope interferometer. I can see like the rings, and then as I slowly walk towards it, I can see like it's sort of that same bullseye like disappearing in the middle, then like going like this.
Ah, yeah.
I'm wondering, is it the same phenomenon? Like, or is it different?
You mean a screen like the metal mesh?
Yeah, where it's like full.
So it's slightly different. It's not, this is a different kind of interference. It's interference, but it's less sophisticated.
Okay.
So you can actually take, if you have two metal grids, you can just kind of like slide them in
Mm-hmm.
or hold them apart a little bit, and you always see this weird interference. So that's like an amplitude interference, whereas
Okay.
here we're talking about electric fields that need to interfere, and so that's.
Right. No, I just.
But,
Okay.
um,
It was interesting. So I was like walking. There was this one particular window, and I would like walk towards it in front of Pico, and I would just see this like huge bullseye pattern. And it was the same thing as from 108.
So I think it's called the Moiré pattern.
Okay.
So look at it this way. Let's say the grid is like this,
Mm-hmm.
okay? So, and let's say it's really small, so you can only see it when you're really close.
Mm-hmm.
Now, let's say I'm in the back of the room.
Okay.
I can't see the small squares,
Right.
but I can see this size square,
Right.
and I can see
okay.
this size square.
Okay.
So the pattern
Yeah.
changes as you get closer because of the resolution of your eye.
Okay.
So because you can't see that these two lines are not overlapping, you see them as one, and you start to see weird, like, your eye just can't make out the pattern, and so all of a sudden it just blurs them. And so as you get farther away, the pattern changes. As you
Okay.
get closer to the pattern
So if
changes.
you're walking, so since I was walking at a constant pace, I sort of see like the same
Yeah.
changes in.
Yeah.
Okay.
Yeah.
Interesting.
Yeah.
Okay.
It's real. Yeah.
Okay. That's
It's cool. Yeah, I think if you look up Moiré pattern,
Okay.
it talks about it more.
Okay. Cool. All
Yeah.
right, thanks.
See you later.
See ya.